This is an overview of Sentient's digital clone for additive manufacturing software, or DCAM. DCAM allows users to simulate different types of metal additive manufacturing processes to predict part residual stresses, distortion, and microstructure. DCAM also includes Sentient's proprietary component life prediction technology to leverage these simulation results for prediction of component reliability in fatigue. DCAM implements a workflow around projects wherein many different analyses can be applied to a part. An analysis joins a part with a machine, material, and collection of process settings. Users can extend the material and print settings library. DCAM currently supports custom material specifications for titanium alloys, nickel alloys, and steels. Custom print settings may be created for a variety of laser powder bed fusion and directed energy deposition machines. The process simulation module is used to predict the residual stresses and distortion of parts built using additive manufacturing. Results are available both before and after the part is removed from the build plate. Users can view the predicted displacement vector and strain and stress tensor components. The microstructure simulation module is next. Here, a user can specify the volume of material for which to predict the microstructure. They can also choose on which planes the microstructure should be predicted. There is randomness in these predictions, therefore, the user can choose how many different microstructure samples to produce to capture this randomness. In post-processing, the user is able to see the grain size distribution measured in each plane for which a simulation was requested. Furthermore, for each individual microstructure that was generated, the user can see the grain size histogram in addition to a view of the grain morphology. The grain morphology plot is furthermore interactive, so the user can explore and experiment with the microstructure. In the fatigue simulation module, a user is able to select one or more of the predicted microstructures to use for virtual fatigue testing. Material cleanliness and porosity are directly specifiable. The simulation runs on large servers on AWS to produce results efficiently. In post-processing, a user is able to view the computed failure times on an SN curve plot. At each load level, a user is able to conduct and visualize a Weibull analysis. Also, animations of the initiating crack and crack growth are available in the software as well. Finally, there is a batch analysis module, which is for process optimization purposes. Currently, users can perform process optimization to minimize porosity. Here, a user can specify the variables and define their ranges. Then, a user will import porosity values and corresponding parameters from 3 different scenarios for calibration purposes. In post-processing, the user is able to plot the porosity map in the defined ranges and obtain the optimal process window. The user is also able to examine individual simulation cases in regards to relative porosity level. These are the primary features of Sentient's digital clone for additive manufacturing.